just talked about calculating kinetic energy, it would be tempting to say, okay, now we're going to talk about calculating potential energy. But in fact, in order to calculate potential energy, we have to actually ask first the question, when can you calculate potential energy? So when does potential energy make sense? And the answer to that is actually it only makes sense for interactions which are what are called conservative interactions. And what a conservative interaction is basically one where if you think about, say, starting with the object at one location and moving the object to another location, right? So if I go from point A to point B along some path, and then I go from B back to A along some other path, that the amount of work that I have to put in along path 1 is equal to the amount of work I get back along path 2. In other words, a conservative interaction is one where the work is path independent, and path independent actually means a couple of things. It means, first of all, that it doesn't depend on what route you follow, and also that it doesn't depend on what speed you go along that route on. So it's only a function of position, right? Or the force is only a function of position. That's sort of got to be one component of the force of the interaction being conservative, and the second component of it being path independent is this idea that the work doesn't depend on which way you get from point A to point B. So I'll give one sort of example of a non-conservative force. Pretty clearly, friction is a non-conservative force. You know, you've already done this sort of example of how, depending on which way you get from point A to point B, if I push a coin this way, it takes less work than if I push a coin via some roundabout circuitous route. So a non-conservative example would be friction, right? On the other hand, gravity is an example of a conservative force, and let me sort of show you a sort of simple example of that. If I think about just being at sort of close to the Earth's surface, if I've got some mass here, right, and I want to move it from this point A up to this point B, right, pretty clearly one option would be to go straight up there, right, and I would do a certain amount of work to lift the object, right. If I were to let the object go, it would drop back down to the ground, and the kinetic energy of the object when it got back down to the ground would be the same as the amount of work that I put in initially. Furthermore, the amount of work that it would take to get from point A to point B would be the same for this path as it would be for this path, because as you can see along this part of the path, gravity points in that direction, dx points in that direction, so there's zero work along that part. This part of the path has the same amount of work as this part. This part of the path has the same amount of work as this part. This part has zero work. This part has zero work. This part has the same amount of this. So the work to get from point A to point B along this path is the same as the work along that path. So gravity is an example of a conservative force. So in order for potential energy to make sense, and we're going to get to calculate how to calculate it in the next video, you need to have it be a conservative force, and there are some forces for which it doesn't make sense, like friction. There are other forces, for example, gravity, for which it does make sense. In the next video, we'll first talk a little bit about how to decide whether or not a force is conservative, and then we'll talk about how you can actually go about figuring out what the potential energy is associated with a force.